The method of detection matters when preventing American foulbrood from spreading. Apis mellifera are a eusocial insect that are also known as the Western or European honeybee. They are essential for the ecosystem for use of widespread pollination. They contribute to plant biodiversity, the quality of produce, and produce natural products that support human immune system and the economy. But just like other beings, they are susceptible to diseases. American foulbrood is a rapidly spreading deadly bacterial disease that infects the brood of a colony. AFB is caused by the pathogenic bacterium Pannibulus's larva that affects only the larval stages of honeybees by infecting them 12 to 36 hours after hatching and spreading via spores after death. AFB can cause the hive to weaken due to progressive depopulation. However, the spores do not have a significant effect on adult bees' midgut when ingested, so spores are harmless to adult bees. The adult bees operate as an asymptomatic carrier of the spore while they perform various nest tasks. In addition, the adults can also act as a spore vector. They can spread or pick up the pathogen due to drifting or robbing behavior among different colonies. The bacterium is characterized as having highly resistant spores that can last 50 plus years. So once it has been spread, the bacteria can't be killed by medication. The hive will typically be burned, including live, brood, and adult bees. So this is why it's such a fatal bacterial disease. My research question was, how is the method of detection important in preventing AFB from spreading? AFB can be detected from several different methods. Culture techniques allow for positive identification of Pannibulus's larva being detected even when no AFB symptoms are visually observed. Spores can be detected by extracting honey, for instance. Culturing, however, can also have complications because it may not show the current disease status of the colony, but rather the disease status from when the sample was collected. Culturing honey samples, for instance, can give false negative results. So in this study, when conducting AFB testing by culturing honey versus the hive debris or testing live adults, the honey examination only showed a moderate accuracy in detecting whether American foulbrood was present. So from this study, it was concluded that Pannibulus's larva spore load in materials taken from the hive debris or from adult bees was more useful in detecting AFB risk in a colony. It's relevant for beekeepers to be aware of the practices they take to assess the risk of AFB in a colony. They should be implementing the most accurate methods of testing in order to prevent the loss of their bees and the spread of the disease. Colonies can also suppress and spread symptoms due to hygienic behavior, where they will clean out the diseased and dead larvae while also spreading the spores. Because adult bees are carriers of the disease, they can be used for identification of the disease within the colony. This study attempted to identify the American foulbrood early detection threshold by analyzing the bacterium spores in adult bees so that they could prevent AFB earlier on in detection. Honeybee samples were taken from 44 colonies belonging to 8 different apiaries in different geographical locations from one another. Colonies were sampled if AFB symptoms were present or if the hive seemed healthy. In an apiary where all the sampled colonies showed the clinical disease symptoms, the average number of spores per bee was significantly higher. There was approximately 5,200 spores per bee for San Giovanni and about 4,500 for Carbonia. In the apiaries where there were no symptoms of the disease, the mean level of spores varied per bee. For instance, 14 in Brachita 1, about 1,800 in Brachita 2, and 438 in Capocachia. If counting the colonies with clinical symptoms as one group, the average number of spores per bee was about 4,600 versus 274 for colonies with no symptoms. This figure is important because it shows how many spores are present within each of the colonies and apiaries, regardless of whether the disease was visually present or not. This gave the beekeepers and scientists more relevant and accurate data on the risk of the disease within the colony. Taken from the same study, the average number of spores per bee in colonies showing symptoms was about 3,031. Colonies with no symptoms showed an approximate of 1,600 spores per bee. This indicates that there is a threshold of around 3,000 Pannibulus's larvae spores per adult bee. This helps represent the threshold for when clinical symptoms in the colony are likely to appear. From these numbers, this indicates that even if a colony may not appear to have spores causing the disease to be present, there are thousands of spores being spread around, causing a larger problem in the very short run of time. The study suggests that adult bees should be used to determine the actual health status of the colony by identifying the spore load of the bee. It's also important to note that the threshold was 3,000 for this study. However, it can increase or decrease based on different factors like the size of the colony, the type of bacterium strain, and other factors. By identifying the spore load and health status of the colony through adult bees in the colony, time-consuming microbiological cultures and colony-forming unit counting can be skipped. Early spore detection in adult bees can be helpful in determining the actual risk of the symptom development by the pathogen. Adult bee spore load is also helpful in perspective of disease prevention, because they can be used to identify the health status of asymptomatic colonies and slowing the spread. It's important to use the most accurate and up-to-date testing information for detecting American Foulbrood. Even healthy colonies can be very sick, but not show the apparent signs, especially if they are larger. Identifying the spore loads per adult bee is a great method in identifying the current risk assessment of American Foulbrood spreading in a colony. American Foulbrood detection is significant for preventing the spread and protecting bee colonies from dying. Understanding the correct and most efficient methods for detecting the disease in hives can prevent them from being burned, can lower the cost of detecting the disease, or spending money on having to replace disease-ridden colonies. This can also improve the biodiversity by keeping colonies healthy and thriving year-round. These are my citations. Thank you.